welcome back to my math teaching today. In this topic today, I will show you how to find the area under the curve using the concept of sigma notation and the limit of the sigma. Find the sum of area using basically the same like REIMANN sum area where we divide the region under the curve by the rectangle strip as the diagram I show on the board. So let's find out how we're going to examine this problem. My first question to you is, if I draw the curve and this curve has the equation of y equal x to the power 3 plus x, and I divide this, and they want us to find the region under this curve from 1 to 4. And if I divide the strip by 1, 2, 3, 4, 5, 6 rectangle, and my question to you that with a simple question like this, why don't we just calculate the width of each strip here, which is turned out to be equal, and we calculate, we look at the diagram when we say, okay, from 1 to here, maybe y1, y2 unit, 3 unit, 4 unit, 5 unit, 6 unit, up to here, maybe the length from here to here is 6 unit for the y. And for each length, we'll be able to use the symbol scale diagram and calculate it. Why do we bother to look at this problem using the calculus, limit, blah, blah, blah? Why it makes so much complicated method? Do we make math more complicated, or why don't we just look at the diagram and calculate it? Actually, when we start, my answer to you now, actually when we start, we always use the symbol diagram. But in the real life or in any problem, it's much more complicated than this. It means the curve here doesn't have to be this curve, can be any curve, right? Can be a linear curve, a quadratic curve, or a cubic curve like this, or maybe something else. And the rectangle here, it doesn't have to be 6 rectangle where we can divide it and look at it, visualize it, right? It could be more this rectangle. And so therefore, if we don't use the mathematical technique and formula from the mathematician has developed it for us a long time ago, then we'll not be able to calculate the area under the curve with any curves and with any region, and it doesn't have to be from 1 to 4 like that, like we demonstrated here, right? So that's why we learn the basic of math, we learn the basic formula so that we can apply in on situation and calculate it. Okay, so now before I get into solving this question, I have to explain to you the concept. Why do we use sigma notation, REIMANN sum? Why do we use this and use the calculus? Okay, so let me show you why. So let's say if you have another curve, okay? Say if you have a curve, something like this. Now under this curve, let's say the curve go like this, more complicated, something like that, right? And then I ask you to find the area under the region, go from A to B, from this unit to this unit. And I ask you to find this area, right, under the curve. So I mark here A of x. So let's say if I ask you to find this area of A of x, and the region I want you to find from A to B. A and B here to represent for any unit. So if we know B is 6, we substitute B by 6. If we know A is 2, we substitute 2. And we got the unit from B to A is 6 minus 2 is 4 units for the length here, if we know B and A. But in math, usually we put in the general number because we want to give the general formula form, right? It doesn't have to be 6 or 2 like that, so that we can apply it to all the problems. So let's say if I have the same diagram, okay, let's say try to make as much as similar as possible, but actually I just want to mean the same diagram, right? Not quite the same, but you know what I mean, right? Let's say I have another diagram like this. Made to be, and actually this curve here, the same curve, right? F of x, see f of x, same curve. And I want to find this region, A of x. But I'm going to divide this region by, let's say, only 3 rectangles here, right? So from here to here is delta x. If the width of each unit is supposed to be the same, I should make them look the same. Okay, sorry. Right, so each width here is the same delta x, okay? And I just divide it by 3 regions, A1, A2, A3. And I say I'm going to estimate it. I'm going to add the first rectangle here, add with the second rectangle here, and add this third rectangle here, right? And I add them, I find the total area under this curve. Now, with the same curve, but I'm going to divide this curve into a very thin strip. Let's say, divide this into a very thin strip, right? Very thin, maybe even the thinner. Okay, instead of just divide by 3, we'll divide by thin strip like this. Now it turned out a strip here have the same width as well, but I just divided. And forgive me for my very bad drawing, right? So each delta x here a lot smaller than the big delta x from here to here, right? So very small, okay? And I call the n strip. And because the reason I call n, because I don't know how many I divide, I just draw a very thin strip, okay? Now, if you look at the gap from the big area, so this gap here is the error, right? When I add them using the rectangle, I estimate this is the error. Big gap here, right? The actual area underneath the curve is just from here to here, not like the rectangle like that. So this here is a gap, is the error. When I estimate 3 regions, I add them together. And my error is huge, right? Because I divide the rectangle is too big. But if I divide the rectangle is very small, like this, what would happen? It turned out each gap here is no longer to be the gap. Very small, right? Each gap here. And therefore, by divide them into small strips like this and add them together, and I call this the n strip because I divided so many rectangles, right? And I don't even know how many ends I divide, but I just make it very thin, estimate thin strip. And if I can add these total of this small total of area together, the gap here is almost disappear until the same like the shape of this curve, the area here. And therefore, the error here go very small, go to 0, almost no error. Then can I when I add the total area of this n area together, I got more accurate result than I divide by huge big gap like this, right? Obviously, you can see that. So therefore, the concept of calculus come from, which means we have to divide this region by so many small rectangle, not three big rectangle like that. When we calculate the estimation of each rectangle here, we have a big error here. But if we divide them by small, we have less error, and our error is almost go to zero. So this gap here almost like not there, right? And therefore we be able to find the area more accurate using the sum of area under the n strip. And so therefore, but if we divide them too small like this, the matter is the numerical values turn out very hard to find. Like if we don't have the way of integration or derivative, or like if we don't have those things, we turn out like how we're going to find if we divide this n strip into 100 or 1,000, or and that's why we have to learn the sigma notation, and we have to learn the way of how we can get away with these small error, right, and find the area on the curve as much as accurate possible. So we're going to use the sigma notation using the adding the total area under the curve when we divide the region into the n region, and the n here is a numerous regions. It could be 100 regions, or it could be 100 strip or rectangle, or 1,000 or whatever. And therefore, to find the numerical value, we have to find the limit when n approach to a big huge number of infinity. So when n strip here go closer and closer approach, never be, but approach, right, to infinity. So when we say n strip here approach to infinity, then find the limit of this, right? When n approach to infinity, when n strip here approach to infinity, and we find the sum of the total area here, when n here could be 100,000, we divide this by x coordinate here, xi1, xi2, xi3, and so on, right? I1, I2, I3, and I4, so on. If we divide it like that, then we find the limit when n approach to infinity. And we will find the limit of delta x, which is the width of each rectangle here, time with the height of each rectangle. And the height of each rectangle is just the function, whatever the function it is, we calculate the height based on that. Then when we do this, we'll be able to find out more accurate numerical value of our area, right? Okay, so that is about the concept. Now, how do I find the unit from A to B? Again, we're going to represent A by B by general number. So we just say, therefore, we have a formula of delta x will be equal B minus A. So if B is 6, B minus A is 2, 6 minus 2, we got 4 units from here to here. And we divide this interval under n strip. So that is give us the width, the delta x width here of each width here, right? So we develop the formula to find the delta x by that formula. So I'm going to say here delta x will be equal to B minus A divided by n. And we represent B by any unit in here, right? minus a divided by n strip. It's very thin strip, small strip. Now let's understand that we're going to use the right hand side, right, of each rectangle here to find out the height of each rectangle. Remember, the formula for each rectangle is multiply the width with the height, or the width with the length, right? The length in here we call a height. So each height here is changing according to the function, right? So the height is changing from small to bigger and bigger, or from bigger to smaller, depend on the function, right? Whatever is different. So the height here for each of them are changing according to the function shape, right? So the height is vary for each rectangle. The width will be the same, the delta x here. The delta x is just use the second coordinate, subtract the previous coordinate, right? So if this is coordinate 1, coordinate 2, so we say x2 minus x1, we get the length of the width. x3 minus x2, we get from here to here. x4 minus x3, we get from here to here. And we know each delta x here is just the same, right? That's our purpose when we divide to the n number. Make sure each width here is the same, right? The height have to be changing according to the function, but the width is the same. So keep in mind all of that concept before I get to how to solve this problem, okay? So basically, to find the area of each rectangle here, we use delta x times with the height, and the height of each rectangle based on the function f of x function, like this, right? In this case, it will be this function f of x like this. In another case, the height of this function will be this function. If we call this is g of x, then it will be the height of g of x, right? Based on x coordinate, we calculate the y coordinate for each rectangle here, right? So each height here, let's say this is height 1, will be on the y1 here. Height 2 here will be on the y2 coordinate here. But the y2 coordinate is the length of this height based on the x coordinate of this, plug into the function to find the height shape according to the function. So let's say this from here to here is unit 1, right? And on the way from 1 to 4, we want to find the region from 1 to 4. And each region here, I divide it, right, using the formula b minus a over n. So b is 4, minus a is 1. So delta x will be equal 4 in this diagram, 4 minus 1. B minus a is 4 minus 1 divided by n, which is equal 3 over n. So delta x equal 3 over n for each strip here is 3 over n. The distance from here to here is 3 over n. The distance from here to here is 3 over n. The same for each width, right? So this actually is the width of this rectangle here. The width is this number for each of them. But the width is different from the coordinate, right? Make sure you know that, right? Because from the diagram, we can see that from 0 to here is 1, right? Unit. Then the xi, the first xi here is the coordinate of this x here, right? The point here I mark here, the coordinate here is 3 over n, which is we calculate from 0. So 1 at 3 over n is the x coordinate all the way from origin 0 to that point, right? So the x coordinate of this point is 1, which is 1 unit here, adding with the little 3 over n here. So therefore, I mark the arrow here from here to here, right, is the coordinate of 1 at 3 over n for this coordinate, the first xi coordinate. So then the second xi2 coordinate here, right, xi2 here will be the same from 1 here to this. So this distance is for the second coordinate, right? And it will be 1 adding with, so up to here we have 2 of 3 over n. So 2 times 3 is 6 over n. So 1 adding with 6 over n is this second coordinate all the way from here to my arrow here, right? Similar, from here to here is unit 1 adding with 3 times 3 of n. So 3 times 3 of n is 1 adding with 9 over n. So that's why I mark this coordinate here is 9 over n, 6 over n, and 3 over n. All of them will be always count from the 0 to here because we use the right hand point, the right hand side of the rectangle, right? We don't use the left side, right? We start from the right hand side. So from here to here, this coordinate of x is 1 at 3 over n. From here to here, the coordinate of xi2 is 1 at 6 over n. And from here to here is the coordinate of xi3 be 1 at 9 over n. So therefore, I'm just saying here, say x1 will be equal 1 at 3 over n, right? x2 will be equal 1 at 6 over n, and x3 will be equal 1 at 9 over n. And this pattern will continue until xi coordinate will be equal 1 at with the delta x is 3, right? Time with the number n of I here, 3i over n. So if I is a 2, then we got 6 over n. If I is 3, we got 9 over n, so on, right? So that is the xi. So now, let's frame this is the coordinate of the x coordinate of this scenario, okay? Now, we also understand that if we want to find the area of each rectangle, we use the formula of, so area equal length times width. In this case, width we call, width times length. In this case, we call width times height. And what is our width? Our width is delta x. What is our height? Our height is shaded, by the function f of x of I, right? So whatever the coordinate x here, we plug into the function y here to find the y coordinate. So this is y2, the same like the height of this rectangle. And this is y3 and yi, so on, find the y coordinate of this rectangle, right? So we say the sum of our area will be equal sigma notation when n approach to infinity, right? And I equal 1 here. And this formula, delta x times with the function of f, x of I, to find the height of each rectangle, okay? And the delta x is never changed, right? Each delta x here is equal, delta x equal 3 over n, okay? So now this concept is clear. We know each rectangle calculate by width, and our width is 3/n in this region, right, from 1 to 4, and our height is the function f of x based on each coordinate here. We plug into the function to calculate the y coordinate of each rectangle, and the y coordinate of each rectangle is the height of each rectangle actually, right? To time with the width here. So I hope that I explained very clear about this concept to you to find this complicated topic, okay? Now, you will see it getting complicated when we use sigma notation and blah, blah, right? And that's why I want the first concept have to be clear, and I repeat it so many times, and forgive me for my redundant talking, if I make any, okay? So let me erase this bar and continue with this concept to show you how we're gonna use this concept to find the numerical value of this using the n sigma notation and the limit of dividing the subregion into the n strip, right? Try that. Okay. So let's get right into the problem solving. Okay, so how do we going to find the area of this? So let me try to use a little space here we have so we can save our room. So our area, right, will be equal to the sum of all the total area, and the n go on top, and I equal 1, and we'll use delta x. Now we're going to substitute the delta x. Delta x in this case is 3/n, right? Use another pen. Okay, I order my pen from the Amazon, and it's not derived yet, so I don't have enough pens for me. Like they ran out the ink very fast, and I just realized after I record the data, I realized that I need the black pens. It will show it more easily than I use any other color, but I don't have anything left. I have a color, so please, sorry, forgive me, like if my handwriting is not clear, but I think that I hope that my my Expo dry eraser, my Expo pen will come soon after a week, so I have enough pen to show you with the better ink on the board. Okay, so sorry for my disorganization. I didn't, like you learn as you go with, right? So I didn't know that the other color didn't show up very well, because when I stand outside, I look at very well, very clear. But when I record it in the Zoom, I realize that the color doesn't stand out. Only the black ones stand out with the white bar like this. So forgive me if you didn't see my handwriting very well, but I will try my best. Okay, for now, until I receive the package from Amazon. Okay, so let's continue with this. So now the area of this will be the sum of all of this, and our delta equals 3/n, right? That's our delta x. Time with our f of x will be the f function, and the x coordinate is 1 from here, plus with 3i/n. All of them follow the function to the power 3, right? Adding with the x coordinate itself, which is 1, plus 3/n. So all of this will be the sum of our area, okay? The region from 1 to 4. So now, let me, so let me calculate that for you, okay? So now I'm going to expand this, right? Now to expand this, I need to remind you about if we have A plus B, all of them to power 3, the formula to expand this bracket will be A to power 3 plus 3A square B plus 3AB square plus the last one to B to power 3. So our sigma notation, and we're going to take the limit, right? So we say limit when n approach to infinity, and our sigma notation n I 1 here will be 3 over n times with our x coordinate is this coordinate 1 plus 3i over n. All of this will power 3 using this function, right? Adding with 1 at 3i over n for the x coordinate here, right? So the whole thing here actually is our formula. Now, keep in mind that this associates with A in this bracket, and the whole thing here associated with the B in our bracket, okay? So we're using this numerical value, apply this expansion for this bracket when we take it out, okay? So now let's find out how it looks like. So that will be called limit of n approach to infinity 3 over n times with 1. I'm going to expand this bracket, sorry. Yeah, times with 1 to power 3, right? A here is 1. So 1 to power 3 is just 1. Adding with this, 3 times 3 is 9, right? 3 times 3, because the a square will be just 1, doesn't matter. So the b here is just follow the formula. 3 times with 3 here is 9i over n. So adding with 9i over n. Add this, the third term will go this way, right? So we're done with this term, we're done with this one, now we go for this. So the third term will be 3 again, follow the formula. 3 times 1, right? A is 1, so it's 3, times with b squared. So this number will be square, and square of this will be 9i squared. 9i squared times with 3 will be 27i squared, all of them over n squared. Adding the last term will be just this b to the power 3 will be 27 again. 3 to power 3 is 27. I to power 3 over n to power 3. So we're done when we expand this bracket. However, this still there, so we're going to add this here. 1 at 3i over n, and we close the big square bracket. Remember, this is delta x, right? The width. The width here will distribute into the first bracket as well as distribute to the second group here when we remove the big square bracket, right? So now I'm going to remove the big square bracket, and don't forget we still have a sigma notation here, which is I should write in sigma notation. So n here and I 1, okay? So this still in the sigma notation. It's not removing yet, okay? So now I'm going to distribute into this. And don't forget, we still have a limit of n approach to infinity. That's always like that, right? Okay. So I'm going to have to use another color. Okay. So I'm going to, so that will be equal limit of n approach to infinity. We'll distribute up to h here. Okay. So we still have a sigma notation. So 3 times 1 is 3 over n, right? This number times with that number. 3 times 9 is 27i over n squared, because n1 times n1 here to n to power 2, right? Adding 3 times 27 is 81i squared over n to n squared is n to power 3. Adding 3 times 27 again, so 81 I to power 3 over n to power 4, because n1 times n3 is n power 4. Adding this number have to distribute to here as well. So that will be 3 over n again. 3 over n times with that will be adding with 9 I over n. Okay, so that's our expression under the sigma notation after we expand on this, right? So now you will see why I said this topic is complicated, right? But be patient, bear with me. I do very slowly, step by step for you to see, right? So now I'm going to say, that I'm going to split it, right? We'll split it, okay? So still limit of n approach to infinity. Split this. So 3 over n. I am going to actually simplify this expression, right? So 3 over n, 3 over n. These are the like terms. I add them together. So let's still put in the sigma notation in general. So I have 6 over n adding with this one, right? 20i. This is 9i. So these two terms are the like term. I'm going to add them together. So I got 36i over n squared. Adding, you see different term. I cannot add it anymore. So just leave it like this. 81i over n to power 3. Adding with 81i to power 3 over n to power 4. Okay, so that's how I simplify this expression become this, right? Nothing changed. So now what I'm going to do is I am going to split it, right? I'm going to say this will become limit of n approach to infinity, and that will be equal 6 times with the sigma notation I 1, and this is 6 times 1, right? And this is 6 over 6 over n. Okay. Adding, let's split this. Remember, anything here I can bring outside the sigma notation. So we'll say 36 over n squared and bring outside. And in here, I have I number, right? This is 36i. Adding with Z81 over n to power 3 and sigma notation, and this is I1. We'll put the I square in here. And I'm going to bring this outside, 81 over n to power 4, and sigma notation n I equal 1, and this is I to power 3. Now, why I do like that? Why I have to split it like that? I'm going to show you why, okay? If you look at the past, I show you, right? We already proved this formula. We know that if we have a sigma notation, which is the sum of natural number, if we have an I, this is the formula. This left side equal the right hand side, equal the sum of this, right? If we have an I square, this formula apply for the sum of I square. And if we have an I to power 3, this formula on the right apply for the sum of the I natural number I to power 3. And that's the reason I want to use this formula to apply for the I here for this one, and I square here for this one, and I3 here for this one. And that's why I split it like that. And I don't bother to prove to you this anymore because I have proven it to you through my video, my previous video. So if you register into my course, you have the set of all of this notation reconnect together. If you forget, you rewind the video to go back and you understand better, you remember better. If you just watch my video on the YouTube, that's great. If you can find my video and connect them together. Sometimes we have a randomly, right? And sometimes one of my video even will not show up on YouTube because we have millions of people watching, and each people have a different video and randomly pick up it very hard. And that's why I developed this course in my, underneath the course online. In the course curriculum, I developed it myself. And I went through with you very simple, very concrete, clearly, slowly, explaining step by step like this to all of you. And in my course, everything is laid out, is very detailed and very clear like this, and connect them together. So if you register into my course, you can understand the whole picture rather than just seeing it randomly like this. And it went into your mind, it's gone, you know. But if you have a record of it and you look at it, so it's a very, course online is a very good education, qualified education to all students, because we be able to watch ourselves teaching. We change it, we replace it, we edit our video until the best for you to see. And also, we develop the course using our expertise area. I major in math, right, in university, and I went through this. I developed it for my course because I love math and I want to do it, right? Now, randomly, I knew that in BC teacher school, sometimes they put the history teacher teach English because they couldn't find the teacher to teach the right subject area. So when they hired me, sometimes I missed the job. I didn't have the qualification. They asked me to teach physical education combined with something like English, or, you know, like sometimes a little math of grade 8, and then combine with teaching like physical education. Now, can you imagine that I didn't went through the high school in here for the physical education, and I have to teach physical education to students, which know better than me the subject knowledge, and therefore the lack of expertise area into our system of teaching is true. Sometimes it's just English teacher teach history, sometimes social science teacher teach math? How student going to understand this rather than now I don't know in US usually they hire the teacher under the subject area, but in Canada I knew that the fact that I went through failing so many interviews because they don't hire me for teaching math. They hire me teaching social when they need a social teacher. They hire me for teaching English when they need an English teacher. And therefore, you don't get qualified education, to be honest with you. So if you register to my course and you follow my method technique clear step by step, you will understand a lot better. And I don't say every case is the same, right? I'm just talking about my scenario situation. Now, maybe some other teachers, they're lucky than me, right? They be able to teach the subject they like and their own expertise, maybe in some case, and in other case different, right? But I knew that from my experience, I knew that it's true that sometimes teachers were assigned to teach different subject area that they don't know much about it in Canada, basically, right? So, okay, I'm not going to talk into the political area anymore. I want to stay away a bit and just focus on our lesson now. And sorry if I wander around a little bit, okay? Anyway, so I'm going to continue with this notation. So I'm going to combine this, okay? So I'm going to bring it down as much as I can like this from the sigma notation, and I'm going to apply the sum of natural number in here, right? So let's get rid of sigma notation now. I'm going to bring it down. Limit of n equal to infinity. And I hope that you still can see this handwriting even though I use a different color. Okay. So I have 6 over n, right? When I bring the 1 out of the n, I make sure this is 1n, right? Because this is the sum of all the natural number of number 1. And however n interval is, this 1 is called according to n. So this is 6n when I bring it out, 6n over n. Adding with 36 over n squared time with, I'm going to use this, substitute by the formula we learned for the I natural number, which is n times n plus 1, right? And all of this divided by 2. Adding with 81 over n to power 3 and time with I square. And I square is, the formula is n time with n plus 1 for I square time with 2n plus 1. All of this over 6. Adding with 81 over 4, over n to the power 4, time with the I3 turned out to be the n square, time with n plus 1 square. All of this over 4. Okay? So this is when we bring out from the sigma notation. We apply the I square for this formula. We apply the I for this formula. We apply the I to power 3 is this formula here. Okay? So now I'm going to have to erase some bar on the top here to continue because I want to keep this, or I can erase this to continue with our, I just want to keep some of this here so that you reconnect with the concept, right? So I'm going to just erase the, I think all of this here is, we need to keep it because that's the concept we need to remember. So I'm going to erase this on the bottom here, on the top here, so we get the room to continue with my work. We should do the last one for now. We should leave the last one to reconnect, okay? Okay, so now from here, you're gonna go up here, okay? So maybe I should draw the line like this. And I will say the limit when n approach to infinity and 6n over n. I want to use a better color, but they seem to run out of ink very quick. I'm not use anymore. Okay. So we have 6n over n. Let's just leave it for now. 6n over n, adding. Okay, so this one, I just want to show you how we cancel it, right? So you see this is n square and this is n. So this will gone and that will become n1 down here, right? 36 over 2. So 36 divided by 2 is just 18, right? So we have 18. And underneath here, we still have an n. Time with this n will gone because we cancel with this, right? So down here become n to power 1 and this gone. We have n plus 1 in here. But I'm going to manipulate a little bit. I'm going to bring this n underneath here, okay, instead. And I'm going to take this out. So I'm going to put them like that, right? Now the next one, we'll say this is 81 over 6. So add with 81 over 6. And the n here, again, will cancel with the n3 here. So this will left with n squared. So this will be n squared down here, right? And on the top, this gone. So we left with this bracket, n plus 1 times with 2n plus 1. Now, instead of put n squared here, I'm going to split this underneath one bracket here, underneath one bracket here. I'm going to split it. We'll bring this inside, but I'm going to split this. It will become n to power 1, and underneath here will be another n to power 1, and therefore this gone. So I bring the n square into here, okay? Now, why I do like that, you will see. The next one will be adding with this one, 81 over 4, right? And so this 4 here. Now n4 here will cancel with n2 here. So that left with n square again. So underneath this will be n square. And we have n square cancel, so the whole bracket here will gone. And we left with n plus 1 for this bracket. Outside is square, right? Okay. Now again, I'm going to manipulate a little bit, okay? So you see this n square, and this is the whole thing here is square. So therefore, I allow to bring this n square going here. Okay, so okay, so this n square cancel with the n4 here. So I left with the n plus 1 on the square over of the n. I'm going to bring it in here, and therefore this is gone, right? Yes. Okay. So now you will see why I do like that. So now the next level will be n limit when n approach to infinity. We're going to simplify a little bit. So this will be gone, and divided by n gone, right? So just 6 adding with 18, n divided by n will be just 1, adding with 1 over n. Adding 81 over 6 times with n divided by n will be 1, adding with 1 over n. Adding with 2n divided by n will be just 2, adding with 1 over n, right? So I convert this into this pattern. Now, why do I do like that? If you remember back into my previous lesson about limit, we find out any number 3 over this equals 0, right? 4 over this also equals 0. If you have 1,000 or million over this, all of this is just 0. And therefore, I lead it to this pattern so that I know that this 1 over n is just equal 0, right? Regardless the top, what number. You have a numbers on the top smaller than the bottom. The bottom is infinity when n approach to infinity, right? So when this n go to infinity, this number down here is huge. And 1 divided with huge number, this whole thing here just becomes 0. This whole thing here just becomes 0 like this. This whole thing here becomes 0. So therefore, I have to lead them in terms of this pattern, right? So we call this a algebraic manipulation. Just take time to practice, right? So now, say limit of n approach to infinity, this becomes 6, adding with 18 times with 1, because this term becomes 0, and 18 times 1 is just 18, adding with 81 over 6, times with 1, because this becomes 0, so 81 over 6 times 1 is just 81 over 6. Adding, the last term is, So this is 81 over 6 times 1 is 81 over 6. Wait a minute. Yeah, this is a mistake. See, be careful, right? This is multiply, not adding. So that will be 81 over 6 times 1. 1 times 2 here, this will become 0. So 1 times 2 is just 2. So basically like that, right? Okay. So now we add this and see how much. So you see the whole process, when we be able to cancel out and use the limit concept, we'll be able to summarize them underneath the numerical value. And that's only calculus can do this. I don't know if I can, anyone can do it better than calculus, right? I just learned it and I know how to do it using on the formula, and our mathematician developed the formula for us. We're just using it and we're still struggling. So how we're gonna invent it any more beautiful, I don't know. Okay, so let's cope with reality. Let's say we are regular human and our mathematician is great scientist. Okay, so we're gonna add them, right? Let's see how much it will be. So 6 add 18, this equals 24. Adding with 81 divided by 6. I will use a calculator for this. This is how I do calculator. 81 divided by 6, 13.5 times 2, equals 27. Yeah, so 24 and 27. 24 and 27. Add 6 as well. Okay. Right? No, we already. Okay, how much is this? 6. Do I missing anything? What is that? Okay, so we have 6 here, adding with 18, and that 1, so 18 times 1, yeah. So this is 81 over 6, So this for this, this for this, this for this, this for this. Check to make sure, right? So that's 1 over n, that's right. 2, 1 over n. I'm missing this term. That's y. Okay. Sorry about that. I'm missing this, right? So now let's do this as well. To see 81 over 4 times with n over n, which is 1 again. So that's 1 over n. This is square, right? But however, we know this becomes 0, so we're missing that. So basically, our answer will be 6 at 18 at 81 over 6 cancel with 2 over 3, adding with 81 over 4. Okay, so let's add these them together. So we'll say 81 divided by 3, 27. 81 divided by 4, 20.25. So this is 24, adding with 27, adding with 20.25. So total will be add 27, add 24, 71.25. So now we'll be able to use sigma notation and the limit concept to find the area under this curve. Very accurate because we use the limit concept, use the calculus concept. Okay, so now keep in mind that this is the number, right? Numerical value. We just found it. Now I'm going to show you what if the same question, but we don't use sigma notation. We're going to use the iteration method, which is antiderivative of the calculus, which is the second fundamental concept principle in calculus, right? Remember my first half course, we're talking about the derivative. And we apply a lot in our derivative. We apply the solution, chemistry and physics, and whatever we throw the ball into the air and we find using derivative, right? Now, the second calculus using iteration, right? The opposite of the derivative. So now let's find out that, using that to see, do we come up with the same answer like this? Or do we get different answer? Now, if we get different answer, it means either method, maybe I make mistake, right? When I do the calculation, or maybe because one of the error, whatever and it's easy to make error. Remember, I'm missing this one when I was talking to you, right? And I'm missing the last term, but now I add into it. So now let's calculate using the iteration technique and combine and see if we use our iteration technique, is it work? Is this the same answer or very close, similar, or maybe it's different? Now, if it's different, so it means that you don't trust me. But always trust the mathematician, right? Always trust the mathematician and trust the formula and trust the calculus. Maybe you don't trust me. I'm a bad teacher. I'm just kidding. Okay, so let's find out the iteration, okay? So let's see how we're going to use this area. So now our second, so let's call this our part A. And I want to say, I'm going to use the part B. Find the area from 1 to 4, the same region, using iteration, which is from 1 to 4, right? We iterate from 1 to 4. And our formula for this fx, right, will be called iteration from 1 to 4. And our formula for the function is x3, adding with x, dx. So now let's doing this. Now this absolutely a lot better than this method. But we want to see how both of them look like, okay? So how do we find this one? Antiderivative. So x to the power 3 will be equal 1 over 4. X, we add 1 power in here, become 4. Before we do this, let me remind you. Remember in the previous video, we say the area underneath the curve, right? The area function, and we have to use the function because this area is not a fixed area, right? This area is keep changing according to the curve. And therefore, the area under the curve is the area of the function of x. When we expand this x to the right, right? So therefore, this area is changing, which is the rate of change of the area under the curve. So the derivative of the area under the curve is the curve itself, right? Now, if we want to find the area, we do backward, which is antiderivative, which is integration of this function. Then we will get the function of the area back to the original function of the area. So the area of function will be f of x, right? And big F, let's say this is big F, f of x equal 1 over 4, x to the power 4 instead of 3, adding with 1 over 2, x to the power 2 instead of 1, and plus c, right? That's how we do antiderivative. And I am going to integrate this from 1 to 4. So let's plug in the formula and see what it looks like. So we equal 1 over 4. X will substitute by 4 here. 4 to the power 4, follow expression. Adding 1 over 2. X will be substituted by 4 again, but to the square. Now c, we don't worry about that because we don't know what c is, okay? So this minus going to be the same, but everything here is just 1, right? To the power 4 plus, make sure this is in bracket, 1 over 2, x is just 1 to the power 2. Okay, so now let's calculate it out. Okay, how do we calculate this out? I believe 4 to the power 4 is a big number. 4 to the power 4 is 256. So 256 divided by 4 equals 64. So we're from here to here, okay? So the first thing here becomes 64, adding 4 to the power 2 is 16, 16 divided by 2 is 18, 16 divided by 2 is 8, right? 4 to the power 2 is 16, 16 divided by 2 is 8, minus, this is 1 over 4, and the other one is 1 over 2. So let's say this is 0.25, adding with 0.5. So 64 at A will be 72 minus 0.75, right? So yes, we get 71.25. So actually very accurate. I thought that it would be close, but very accurate actually, right? So now you can see the powerful tools of calculus is we reduce from a big task all of this, right? Even though with this notation, sigma notation method, we already see how powerful it is when we know the sum of natural number and we be able to get rid of on the limit and the n, and finally come up with the numerical value 71.25. But this is a long way of doing it. Now, using the iteration, right? This is a powerful tool in calculus. We'll be able to do it in 5 minutes, right? If we learn how to do antiderivative, we learn how to do all of this, the calculation becomes so much easier and we get the same result. So that's why the purpose of my lesson in this unit, I would like to show you both techniques. The first technique is REIMANN sum area by divide this into sub-area strip and add them together using sigma notation and limit when our strip getting very big number and number getting very huge to infinity, and the strip is getting smaller and smaller, and we add the total area. We get accurate actually, we got 71.25. And if we use a calculus iteration using antiderivative like this, we'll be able to come up with the same result. It means compare two methods. You see, this is, I said that math is fascinating, right? When we figure out the answer and we see that how amazing it is, like when we find out if we use correct and accurate, we get the same answer. So it doesn't matter what method technique you use, as long as we get the right answer, we're okay. Now everybody will refer to do the iteration, right, in calculus, and that's why we learn calculus. And so anyway, this is a long video. I just would like to show you in my course. And this is the second course, calculus level, and it's equivalent to the first year university course in your university. So everyone, if you like my teaching, you like my method, you like the way I explain, very clear, step by step, go very slow, right? And you stay away from social distraction. You can rewind your video, you can watch, relearn, and you have my notes. Put in the powerful MS PowerPoint presentation, stand out and clear to you step by step. You should register to my course and enjoy. Now, I don't charge a lot for the course compared with my labor. To be honest with you, it's nothing. You can buy the dress for 300 and wearing out 1 hour, one time you went to the party. Maybe only when in occasion you need, right? When you have a prom or whatever party. But however, with my labor, you have haircut, you still have to, like paying for it. With all the knowledge I store it from my university, from first level to second level, and everything I knew I went through, I show everything to you. I didn't hide any of my knowledge. So this is, it's nothing. Like if you buy my course, to be honest, a few hundred, not even though it's very cheap, right? You can buy it. I think the first calculus I charge you only 179, I don't remember, like divide by 3 times so you can pay it when as you go, instead of paying the whole thing, right? So allow me to advertise a little bit for my course, right, in YouTube, so that you know that my labor, you learn it from it and you get it value, and it easy to learn, right, this stuff out of it, and you get the good result, good answer. So you, I think online course is very privileged to all of students now. You have this kind of reform education because of the pandemic going on. We always think of something higher, to cope with the reality, right? So now some of you might enjoy online learning. Some of you might prefer face-to-face teaching in the classroom, right? We're not going to abolish on the school building we build is so expensive, right? However, some students might find like it easier to learn with the online like this, face by face, the one-on-one tutoring like this, instead of go to school in a big building with social chat and distraction and anything. I don't know. It's up to some student will refer that way. Some student will like this way. So I hope that at the end, all of the method and techniques we learn like this will combine together and bring out the best in education to all of you. Okay, so thank you for watching. I hope you enjoy it and bye for now.